Hey guys, in this next page, I want to give you a big picture view of how a lot of seemingly random carbonyl reactions are actually all related to each other. And this section is called the nucleophilic addition of solvents. So, in general, all the reactions that I'm going to show you on this page are all connected by one theme, which is that they're induced by the extraordinary reactivity of the carbonyl carbon. Remember, it has a very strong partial positive. So strong, in fact, that that partial positive isn't just going to react with negatively charged nucleophiles. It's also going to react with solvents. And I want to put here in parentheses neutral solvents. So that means that the carbonyl can actually get neutral things to attack it through nucleophilic addition. How crazy is that? Well, these reactions aren't going to happen by themselves. They are going to need catalysts. They're going to need either acid or base catalysts, okay? In general, almost all of these reactions are going to be acid catalyzed, and the mechanism we're going to be focusing on in this section are the acid catalyzed mechanisms, okay? Those are the ones that are the most commonly tested on, okay? And then one general theme about all these reactions that I'm not going to have to say over and over again because you guys will know it, is that they're all fully reversible in mild acid. So you can always use mild acid to go back to the original carbonyl that you started with, okay? Due to the fact that these mechanisms are mostly acid catalyzed, whenever you have something that's an acid catalyzed mechanism, then by definition, protonation should be your first step, and deprotonation to regenerate the catalyst should be your last. So when you're looking at these daunting mechanisms, some of them are going to be like 12-step mechanisms. But when you look at them, at least you should know where to start. You should always think, I should protonate before I do anything else, because it's an acid catalyzed mechanism. So let's go through the list. I'm really just going to be giving you the just the general features here, and then we'll focus on the details in each respective reaction when I go to the reaction videos, okay? So the first one and the easiest one. Guys, ketones and aldehydes are so reactive, this partial positive is so reactive that it can even get water to react with it, okay? So when water reacts in the presence of acid with a ketone or aldehyde, we call that a hydrate. And notice that your product is basically a gem diol. So we would call this a gem diol or geminal diol. Okay? So just keep that in mind. Water, we're just starting it off with like the most shocking solvent, which is that even water reacts with carbonyls to form a gem diol. So meaning that if you have a mixture of ketones and water in your test tube, it's actually not going to be all ketone. Some of it is going to be gem diol because the water is reacting with it, okay? More on that later. Hemiacetals. So hemiacetals are produced by the addition of one equivalent of alcohol. So one equivalent of alcohol will give you something called a hemiacetal. Two equivalents of alcohol will give you an acetal, okay? So hemiacetal, acetal. Notice the difference is that one of them has an OH group and one of them has an OR group. So basically in one of them, you're only adding one OR from alcohol. In the second one, you're adding two ORs from two alcohols, okay? And guys, the name hemiacetal means half of an acetal, because hemi is a prefix that means half, like hemisphere, half of the world, okay? So then we've got thioacetals. Oh, and by the way, guys, these can happen in both acid and base catalyzed reactions, but I'm just going to focus on the reagents right now, and then we'll talk about the mechanisms, like I said, in separate videos. So thioacetals happen when you mix BF3 with SR, or I should have put it the other way, with basically HSR, RSH. There we go. That's what I'm looking for. So instead of an alcohol, notice that it's the same thing as an alcohol, but instead of being an alcohol, it's going to be a thiol group, okay? So RSH times 2. Oops. RSH times 2. Okay? So notice that this reaction is actually very similar to the one above it, acetal and thioacetal. The only difference is that now I'm getting SH groups instead of OH groups, because I'm reacting instead of ROH, it's RSH. That's it. And then the acid here in this case is just a little special. It's a BF3 instead of your normal Bronsted-Lowry acid, okay? Cool, let's keep going. So, what happens if you react amines with carbonyls? Well, turns out that primary amines. So if I have NH2R, primary amines. So primary amines will give you an imine product, okay? So this functional group is called an imine, all right? It's a double bond N with an R group at the top, okay? Now this also works for ammonia or NH3, okay? Primary amines or NH3 is going to give you an imine, okay? Now on top of that, if we react with, instead of NH2R, if instead we add, instead of an R group, we add something else, like for example, a Z group. Now that Z could equal a few different things. That Z could be, you know, another nitrogen. It could be an alcohol, etc. Okay, so there's a lot of different things that we could put there, okay? But if you add something else instead of that R, then you're going to get an imine derivative, because instead of getting the R at the top, okay, now notice this R is what's attached here. Now you're going to get a Z instead. Okay, makes sense? So that would be what we call an imine derivative, because of the fact that it looks like imine, but instead of having an R group, it has a Z group. And finally, we know what happens when you react with NH3, what happens when you react with primary amines. What about secondary amines? Well, when you have secondary amines, so that would be NH with two R groups, RR, then you get what's called an enamine. Okay, the reason this is called an enamine is because you've got an amine part at the top and you've got a double bond, an alkene. So put them together, you get an enamine. Okay, so now instead of just having one R group attached, you have two. Now notice that the orientation of this double bond is really different than the first one. In the imine, the double bond was facing the N, was on the N. In the second one, the double bond is now towards a carbon. Why is that? Well, that's something that we're going to have to learn through the mechanisms. So when we go to the exact mechanisms, you'll understand. But it's essentially the same exact mechanism, just with one final step that's different, okay? That's the biggest difference between them. All right, so that is pretty much the extent of the reactions of solvents with ketones and aldehydes. And notice, I pretty much named every single solvent that's out there. I mentioned water, I mentioned alcohol in every form, I mentioned thiol, and now I mentioned amines, all types of amines. So if it has a lone pair, it can react with a carbonyl. Okay? Now what I want to do is I want to just really briefly introduce what can happen with these reagents. So after you make them, what can you do with them? Well, it turns out that hemiacetals, as we'll learn later, are not very stable. They like to go to full acetals, so they barely ever last as hemiacetals. Only cyclic hemiacetals are stable. Okay, so we'll see that later. So this would be a cyclic hemiacetal, because notice that I've got a carbon that's attached to, you know, it's got an H, it's got an R, and then it's got the OR here, and it's got the OH here. So that would be a hemiacetal, and we're going to have to learn how to recognize these, but that would be a hemiacetal because I've got a carbon in the middle that has an OR and an OH group on two different sides. And this one would actually be stable. But if it's not cyclic, it's not going to be stable. Acetals are used as protecting groups, okay? So acetals, specifically when you have a diol, you get cyclic protecting groups. So notice how this thing is a ring, okay? So we're going to see how later on when we use diols, instead of two different alcohols, when you use a diol, you get a cyclic acetal. And in general, acetals are used as protecting groups. So more on that in another video. Whew. So what happens with, what can you do with a thioacetal? Well, remember that a thioacetal is just a molecule that has a central carbon with R's on both sides, R's or H's, and two SH's, two thiols at the top. Well, it turns out that when you react a thioacetal with a reducing agent called Raney nickel, Raney nickel is going to be able to destroy those thiol bonds and make it into a simple alkane. So it's a form of reduction that turns, essentially, you're turning a carbonyl into an alkane because you're just adding H's. So it's a way of getting rid of carbonyls completely. Okay? Imine derivatives. So it turns out that imine derivatives, when you have specifically, if I were to use the NH2Z, okay, so specifically if I were to have this derivative, more on that later, that's called hydrazone. We'll talk specifically about that later. Remember, this is just the overview. But when you react hydrazone with a strong base and heat, you get what's called a Wolff-Kishner reduction. Wolff-Kishner reduction. And what we find is that a Wolff-Kishner reduction is another way to add hydrogens to a carbonyl. So it's another way to turn a carbonyl into an alkane. So Raney nickel to a thioacetal, Wolff-Kishner to a hydrazone, which is an amine derivative, are really the same reaction in terms of they yield the same exact products, and they're used in very similar situations. Except one is base catalyzed and one is acid catalyzed, because you're going to have to use that BF3 to get the thioacetal. Awesome. And then finally, guys, this is kind of getting way ahead of ourselves, but it turns out that enamines, we're going to find out later, love to react with alkyl halides, okay? They love to react with alkyl halides to form what we call alpha substituted carbonyls. So essentially, I mean, this reaction, we'll talk about it more in the enamine alkylation section of Clutch videos, but essentially you get a lone pair that jumps down, a double bond that attacks the R, basically does an SN2 reaction, and you wind up getting an R group where that enamine was, okay? So this is a huge part of organic chemistry all on its own, is just talking about how enamines love to react with alkyl halides and other types of electrophiles to get alpha substitution, okay? So, guys, I know this was overwhelming, and to some extent it's meant to be. What I'm trying to show you is that all these reactions, you're going to learn them in different parts of the text, but they're all related by the sense of that it's a neutral compound reacting with a very highly positively charged carbonyl-carbon, okay? So now what we're going to do is, now that you've seen the overview, we're going to go into those individual reactions one by one, and we're going to learn mechanisms. It's going to be fun, all right? So let's go ahead and wrap up this topic and start onto the next topic.